Okay, so let's talk about eigenvalues and eigenvectors. So let's say we have a square matrix n by n. And then I have an n-dimensional vector, and I almost forgot to specify that it's not the zero vector, but it's not the zero vector. It could be real, like reals to the n, or it could be complex. Also, the entries of A could be complex. Everything could be complex. And we have number lambda, which could also be complex. If we have A times V equals lambda times V, so on the left this is matrix multiplication, like V is a vector, but it's like a matrix with just one column. So this is a matrix times a matrix. Over on the right I've got a scalar times a matrix. So if I have this, then we say that lambda is an eigenvalue of the matrix A, and that the vector V is an eigenvector. And in particular, lambda and V sort of go together. Like, not every lambda goes with every V. So I say that V is an eigenvector associated with the eigenvalue lambda. How can we find such things? So I'm going to give you a matrix A and expect you to find lambdas and V's that go with that A. So here's the procedure. Well, I'm going to give you why the procedure works first, and then I'll give you the procedure. So here's the equation we're trying to solve, and I'm just going to subtract this over to the left and get this. Then I'm going to sneak the identity matrix in there, because the identity matrix doesn't do anything, so I can do that. And why would I do such a thing? It's so I can pull V out, because both of these terms have a V on the right, so I can pull V out on the right. And then what I have inside is A minus lambda times I. And that actually makes sense, because I can, for matrix addition and subtraction, I can only add or subtract matrices that have the same dimensions. And so, but I'm allowed to do this. This is a matrix minus a matrix. Of course, assuming that I has the appropriate size, because you have an identity matrix of whatever size you want. So we're assuming that it's the appropriate size for this to make sense. And so what we have here is, we would call this a homogeneous system of linear equations, where I have this matrix, and I'm considering V like my vector of variables. And recall that V is not the zero vector, so this is a homogeneous system. By the way, it's homogeneous because the right side is 0. It's a homogeneous system of linear equations, and it has a non-zero solution V, because V is not 0. So remember what singular means. A square matrix is singular if, like, that matrix times V equaling the zero vector has infinitely many solutions. It's non-singular if it has only the zero vector as a solution. So this matrix, since we have a non-zero solution V, this matrix is singular, and we learned that singular is synonymous with having a determinant of 0. So the determinant of this matrix, so here I have it written with absolute value signs, but just to remind you, these absolute value signs mean determinant. The determinant is 0. This equation is called the characteristic equation. This is the equation that we're going to solve to get lambda. And by the way, that determinant, the one that we're setting equal to 0, is called the characteristic polynomial, and it might not look like a polynomial, but we'll see that it is. Anyway, so here's the procedure. I solve the characteristic equation for lambda. And notice that the characteristic equation doesn't have V in it anymore. Like, lambda is the only variable. Like, we're given A, so that's just whatever matrix it is, and I is just the identity matrix. The only unknown to solve for here is lambda. So we solve that for lambda. And then once I know lambda, I go back to the line that does have a v in it because I want to solve for v. And I solve this linear system. And of course, actually, this is going to have infinitely many solutions, like a homogeneous system. If it has even one non-zero solution, it's going to have infinitely many. So there's going to be infinitely many eigenvectors. And in fact, the set of all eigenvectors forms a subspace of an n-dimensional space, and we call that the eigenspace for lambda. So typically, if it's a one-dimensional space, then it's pretty easy. You can just name one vector, and then the eigenspace is just all multiples of that vector. Otherwise, we can give like a basis for the eigenspace. So we do that. And then we know our eigenvalues and eigenvectors. So, quick definition and theorem before I do an example. An eigenvalue has what we call an algebraic multiplicity and also a geometric multiplicity. The algebraic multiplicity is the number of times it's repeated as a root of the characteristic equation. And I know we haven't done an example yet, but I've told you that this thing is called the characteristic polynomial. I assure you it comes out to be a polynomial, and that equals 0. And the way you solve that is by factoring the polynomial. And sometimes polynomials have repeated factors, like you'll see lambda minus 1 cubed or something. If you see lambda minus 1 cubed, I would say that 1 is an eigenvalue with algebraic multiplicity 3, because that's the power, like if it's lambda minus 1 cubed. So that's what algebraic multiplicity is. It's the number of times lambda is repeated as a root of the characteristic equation when you factor that polynomial. The geometric multiplicity is the dimension of its eigenspace, because like I was saying, there's always infinitely many eigenvectors, and in fact, the set of all eigenvectors is a subspace of Rn, and so it has a dimension. That dimension is called the geometric multiplicity. Typically, they're the same. In fact, it's sort of a weird coincidence if the algebraic multiplicity and geometric multiplicity are not the same. However, there are important examples where they're not. One thing that's always true is that the algebraic multiplicity is always less than or equal to the geometric multiplicity. Usually it's just equal, but sometimes it's strictly less than. Anyway, let's do an example. We're going to find the eigenvalues and the associated eigenspaces of this matrix. So, let's go. Characteristic equation is it's the determinant of a minus lambda I equals 0. So I'm writing a determinant. Inside this, I'm going to write a minus lambda I, and I'm going to set it equal to 0. So, of course, I just has 1's down the diagonal. So lambda I just has lambdas down the diagonal. So I'm going to take this matrix and I'm going to subtract lambdas down the diagonal. Okay. So here I have my 3 by 3 determinant. And of course, you know, determinants in general can be a pain. I could do the trick, like the shortcut for 3 by 3 determinants, where I copy this column down here and copy this one next to that, and then I go down, 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 up, up, up. That wouldn't be that bad, but I can do something even slicker. I made my life easy. I did choose this example because I didn't want this to be too much of a nightmare. This is an upper triangular matrix. I have zeros below the diagonal. the determinant of an upper triangular matrix or a lower triangular matrix, any kind of triangular matrix, is just the product of the diagonal entries. So we just very quickly found the determinant of this matrix. And like I said, this is a polynomial. I could multiply it all the way out if I wanted, like, FOIL everything out. That would be counterproductive, though, because I'm trying to solve this equation, so I prefer it in factored form. And here we can see what I was talking about algebraic multiplicity. I would say we have lambda equals 1, and nobody asked, but I will tell this has algebraic multiplicity 2 because this appears twice as a root. That's what I mean. Now lambda equals 2. That just has algebraic multiplicity 1 because there's just this one factor. Okay, so let's find the associated eigenspaces. So let's find the eigenspace for lambda equals 1. So like I was saying, once I know an eigenvalue, finding an eigenspace, that's like finding my v's. So I go back to this, and in practice, here's what we do. I'm going to set up an augmented matrix, because what this is a homogeneous system of linear equations, because I've got 0 on the right. So I'm going to set up an augmented matrix with zeros on the right. And what goes here, it's not quite my original matrix A, it's my matrix A minus lambda I for this value lambda. In other words, it's going to be A, but I'm going to subtract 1s down the diagonal. So 0. Like that. And the eigenspace is the set of solutions to this. Where, like, to be clear, V is a column vector. I can say, and it's going to be 3-dimensional because it's a 3 by 3 matrix. And so it's like in this system, this is like representing a linear system where these are my coefficients of V1, V2, and V3. So let's get this in echelon form. We're almost there. So I've got nothing but zeros in the first column, but that's okay. For my echelon form, I try to get this, looks like stairs. So my stairs are going to start here, then I go to the right until I reach the leading term of my next row. And then I want my stairs to go underneath that. But, well, I would want this 1 to be a 0. I've got this leading term. I want zeros underneath my leading term. So this is not quite in echelon form yet. Let's get it there. I'd like a 1 here. And this is kind of boring, but... So I divide this row by 2. And it's easy to see what happens there. So now my leading term is a 1, but I have not achieved my goal because I want a 0 underneath it. So I'm going to do this row minus the one with the 1 in it. Of course, that's just going to 0 this whole row out. When you're finding eigenvectors, and you're doing this step, you should always have at least 1 0 row. Because you're going to have a free variable. We expect this, unless we've made a mistake. we expect this to have infinitely many solutions. There's got to be a free variable. And there is one. Actually, I guess, right, we haven't quite seen an example like this yet, but let me circle my leading terms. So I've got this, or leading coefficients, I should say. I've got this one, I've got this one, so I would say this column is leading, this column is leading. The first column is not leading. That's what's unusual, or at least we haven't seen an example like this yet, I think. But that makes it free. So, yeah, the way I typically handle this is I call the free variable s, and if I had another free variable, I would say t, and so on. I just go down the alphabet. And then I solve for the leading variables. So this equation, this bottom equation, is going to tell me x3 is just 0. The top equation tells me x2 plus 3x3, but I'll just write 0 because we know x3 is 0, equals 0. So x2 is 0. Or, I'm sorry, I was calling this v1, v2, v3. There we go. But it is what it is. Right, so I'm kind of running out of room here, but so my V is, V1 was S, and then 0, 0. Let me just start a new page here. So my eigenspace for lambda equals 1 is, it's the set of all vectors that look like this, and I can factor my s out. And let's say, yeah, s could be any scalar. So yeah, let me point something out here. We did our job. We don't have to keep making observations, but let me keep going because I like it. The geometric multiplicity was actually 1. So I purposefully chose an example where the algebraic multiplicity, because recall the algebraic multiplicity of this eigenvalue was 2, the geometric multiplicity is actually 1. And, you know, so I had to find a slightly strange example to make that happen. It's not usual, but I wanted you to see it. And, right, how do I know the geometric multiplicity is 1? Well, one way of saying it is just because I have one free variable. Like I've got one degree of freedom, which is my choice of s. A basis of the eigenspace is just this vector. So the dimension is the number of vectors in a basis, and there's just one. It's just this vector 1, 0, 0. Anyway. Let's run through the eigenspace for lambda equals 2. So this is repeating the procedure. I set up a homogeneous linear system. I've got zeros on the right. On the left, I've got a minus lambda, except now lambda is 2. So here's my a, and I'm subtracting 2 down the diagonal. So negative 1, 1, 3. Like that. Like that. Okay. Yeah. Here. Let me just make these negative ones into positive ones. This is not going to take a lot of work. Maybe I don't even need to do what I'm doing, but I like positive ones. So this is an echelon form. Actually, it was already an echelon form. I just kind of prefer positive ones to negative ones, right? Like, here are my stairs. As usual, I do have a 0 row. I didn't have to work hard to get it. It was already there, but we expect that to happen, whether I need to work to get it or not. I have a free variable here. So let me not make the same mistake and call this x3 again, because it's v3. v3 is free, so I'll just set it equal to s. v2 is whatever I get, so that like this is like a negative 2s, but I need to get it to the other side of the equation, so 2s. v1 is, so I've got this is a negative v2, but I get it to the other side of the equation, so it's a positive v2, which is a 2s, and then positive 3v3, so 3s, so that's 5s. So v is 5s, 2s, and s. And we often like to factor the s out. So I can write my answer just like that, but I'm basically done. This is also a one-dimensional eigenspace, which this is the more normal situation because recall, lambda equals 2 had an algebraic multiplicity of 1, and it turns out that the geometric multiplicity is the same. It's just 1.